dear students, Standard 11, chapter number 4, Laws of Motion. So in previous chapter we studied what is motion, and now we have to study about laws of motion. So here first we have to discuss Aristotle's fallacy, right? Aristotle suggested this thing: an external force is required to keep a body in motion. So Aristotle suggested this particular law of motion just with day-to-day observations. But it was false, right? Later it was proved, and therefore it is known as Aristotle's fallacy. After Aristotle's law of motion, scientist Galileo took some precise observations related to the motion of the body. So which type of observations he took, and with the help of those observations he represented the law of inertia. So how he performed experiment? So in his experiment he took two inclined plane as shown in the figure, and one spherical body, when released from the top of the inclined plane, he observed this thing: when the body is moving in downward direction, it accelerates. It implies that its velocity is continuously increasing one. Then after, on the opposite inclined plane, when it moves in upward direction, then it retards, means its velocity continuously decreases. Now here in between these two, motion on the horizontal plane can be treated as an intermediate situation. So with this type of precise observations, he suggested this thing: if horizontal plane is frictionless, then there is no acceleration or retardation of the moving body. It implies that if the body is moving on smooth surfaced, frictionless horizontal surface, then it continues its motion with constant velocity. Then after, he performed second experiment. In second experiment, he took this type of double inclined plane, and in the middle part of it, it was horizontal. So here he observed this thing: from left hand side, if the spherical body is released, then it accelerates, and if the horizontal part, that is the smooth one, if we consider it frictionless, then almost it moves with constant velocity. When it moves on other side, it retards, but the height attained by the body on other side, that is almost the same one, maybe slight less than that, but almost the same one. Then in second experiment, he took the same double inclined plane, but on other side, means on right hand side, the inclination was less. Okay, so again when the experiment was performed, he observed this thing: the spherical body attains the same height on the other side, but to attain the same height, it travels more distance, right? And then after, third experiment was performed with the help of single inclined plane, right? And from upper side, when the spherical body is released, then it accelerates, and when on this horizontal smooth surfaced motion is there, at that time it moves with constant velocity. So with the help of this type of precise observations, he suggested law of inertia. Law of inertia says this thing, if the net external force acting on the body is 0, then the stationary object or stationary body that remains stationary, or we can say steady object that remains steady, and the body which one is in motion continue its motion with uniform velocity, or we can say with constant velocity, right? And this is known as law of inertia, right? Or we can say inertia is nothing but the resistance to change. It implies that body itself opposes any type of change in its state of motion. If body is steady, then it wants to remain in the steady state. If body is in motion, then it moves with uniform velocity and it continue this motion till the net external force is not acting. So this particular characteristic of the body or property of the body, that is called inertia, and that is nothing but resistance in change. Clear to all of you? So past studies related to motion of the body, Newton suggested first law of motion. Actually, Newton's first law of motion, that is nothing but the law of inertia itself. So Newton suggested this thing, every body continue to be in its state of rest or of uniform motion in a straight line, unless compelled by some external force to act otherwise. The same thing, if net external force is not acting on the body, steady object remains steady, and the object in motion continue its motion with uniform velocity. After all, the same thing is this one, right? Okay, so here, see, important thing is this one, the state of rest and the state of uniform motion. These two situations are taken in this particular law. So we can say this thing, this both the state of motion, one is the steady state, means it is with velocity equal to 0, and another state that is with uniform motion means it is with constant velocity. Both the states are identical. How? In both these cases, the acceleration that is 0. So here we can say this thing, force is such a physical quantity which produces acceleration in the body. Clear? When the body is steady, its velocity that is 0, so acceleration is 0. When the body is moving with uniform velocity, then change in velocity that is 0, so acceleration is 0. So both the states are the case of 0 acceleration. So the first law can be represented like this also. If the net external force on the body is 0, then its acceleration that is also 0. Clear? Acceleration can be non-zero only if some net external force is acting on the body. Clear? Now example 4.1. An astronaut accidentally gets separated out of a small spaceship. Acceleration in interstellar space at a constant rate of 100 meters per second square. What is the acceleration of the astronaut the instant after he is outside the spaceship? Assume that there are no nearby stars to exert gravitational force on him. So as soon as the astronaut comes out from the spaceship, right? So at that time, here it is specifically given to you, there are no nearby stars to exert the gravitational force on him. It implies that no external gravitational force due to stars is acting on him. Then when he come out from the spacecraft. So at that time, if we think about the gravitational force of spacecraft on astronaut, so that is very negligible one, very negligible one. We know gravitational force, that is the weakest force, right, in the nature. So it is almost a negligible one. So when astronaut comes out from the spaceship, at that time, now outside it, on the astronaut, there is no force. So when no force is acting, means net external force, that is 0, means its motion, that will be non-accelerated one, or we can say that will be with 0 acceleration. Okay, so in this way the motion is with 0 acceleration. Clear? Now dear students, next topic, that is Newton's second law of motion. Now here we have to understand one important physical quantity, that is the linear momentum, or we say momentum. This one is very important physical quantity because momentum is defined as the product of the mass of a body and velocity of the body. And linear momentum or momentum, we say, that is a vector quantity and it is in the direction of velocity of the body. So the product of mass of the body and its velocity, that is called momentum. So we can write momentum P, that is equal to mv. And when we say mass is the scalar quantity, velocity is the vector quantity, so obviously we can understand here the momentum that will be in the direction of velocity. This one is very important physical quantity because here mass is associated with velocity. See, with simple example, you can easily understand the importance of this quantity. Suppose your friend that is on a bicycle and slowly he is moving on the bicycle. Suppose the velocity that is with 5 km/h, slow. And now if you pull the bicycle, then easily you can stop bicycle with the force applied by you. Suppose maximum force applied by you, that we consider as a constant force. Now imagine, suppose your daddy is starting car and start motion with speed 5 km/h. Now apply your maximum force and try to stop it. Is it possible? No, you will be pulled by that particular car in the direction of its motion. So velocity of both the object, bicycle and car, same one. But due to mass of these two bodies, the momentum of these two bodies are different one. Momentum of car, that is large one compared to momentum of bicycle. Therefore, large amount of force is required to stop it. So this one is very important physical quantity. Now momentum is a vector quantity we discussed and it is in the direction of the velocity. Now from this one we can understand the SI unit of the momentum, that is kilogram meter per second. And from that you can write the dimensional formula, that is m1 l1 t minus 1. Okay. Now experiments shows this thing. If same amount of force is applied to different objects for the same time, then change in momentum for different bodies will be same one. And from these observations, this type of experiments, Newton suggested second law of motion. Now Newton's second law of motion suggests this thing: the rate of change of momentum, that is directly proportional to the applied force to it and is in the direction of the applied force. Okay, so rate of change of momentum of the body is directly proportional to the applied force and takes place in the direction of force. So we can write F proportional to delta P by delta T. Here we introduce the proportionality constant K, but this constant of proportionality that we choose K, that is equal to 1. So simply we can write Newton's second law of motion, F, that is equal to delta P by delta T. Now suppose here we take limit delta T tends to 0. Then we can write F, that is equal to limit delta T tends to 0 delta P by delta T. But this can be represented as differentiation. So we can write F, that is equal to dP by dt. Okay. Now we know this thing, momentum P, that is equal to mv. So in this equation, if we replace P by mv, now mass is constant one. So take it outside the differentiation. So we can write mass into dV by dt. dV by dt, the differentiation of velocity with respect to time t, that is the acceleration. So we can write F equal to ma. So here second law of motion, that is F equal to dP by dt, that is equal to ma, right? So this one is another form of second law of motion. Now here in component form, we can write the second law of motion like this: Fx equal to dpx by dt, that is equal to max. Means the differentiation of x component of linear momentum with respect to time t will give you x component of the force, and that is equal to mass into x component of acceleration. Similarly, Fy equal to dpy by dt, that is may. Similarly, we can write Fz equal to dpz by dt, that is equal to maz. Now, see here, from F equal to ma, we can write the unit of force, that is kilogram for acceleration, that is meter per second square, and this kilogram meter per second square, that is called Newton. So 1 Newton force, that is equal to 1 kilogram meter per second square force. And here we can give the definition of 1 Newton force, or in other words we can say the definition of 1 kilogram meter per second square force. The force which produces 1 meter per second square acceleration in the object having mass equal to 1 kilogram, that force is called 1 kilogram meter per second square force, or we can say that particular force is called 1 Newton force. And from this unit we can write its dimensional formula also, and that is m1 L1 T minus 2. In CGS, we can write the unit, that is gram centimeter per second square. And this CGS unit, gram centimeter per second square, that is called dyne. And the relationship between Newton and dyne, that is like this, 1 Newton that is 10 raised to 5 dyne, right? Now here we have to think about two important points related to this second law of motion. See here, first thing, suppose the force F that is equal to 0. If F equal to 0, then ma that is equal to 0, mass is not equal to 0, means acceleration equal to 0. So here we can say, if the force is not acting on the body, some net force is not acting on the body, then its acceleration will be 0. If acceleration is 0, it implies that we can think about two states of motion. Either the body is stationary or the body is moving with constant velocity. So this one is consistent with first law of motion. Clear? And Newton's second law of motion, that is vector law, because here force, momentum, acceleration, all the vector quantities are appearing in this law. Clear? Now example 4.2. A bullet of mass 0.04 kilogram moving with a speed of 90 meter per second enters a heavy wooden block and is stopped after a distance of 60 centimeter. What is the average resistive force exerted by the block on the bullet? Now see here, mass of the body that is given to you 0.04 kilogram, initial speed that is 90 meter per second, the distance covered by the bullet in the block that is 60 centimeter, so that is 0.6 meter, and after covering this much distance in the block, it is stopped. So final velocity, that is 0. And now we want to calculate average resistive force. Now force F equal to ma. In previous theory we studied this thing, right? Mass is given to you, but acceleration is not given to you, right? Here we consider the acceleration, that is constant one, and actually that will be the deceleration because velocity is continuously decreasing one. Now here we can use the equation v square minus u square equal to 2as. So v that is 0, u that is 90, to a that we have to find, and s that is 0.6. All are given to you. So we can write 0 minus u square, that is 2as, a that is minus u square by 2s, substitute the values. So minus 90 square upon 2 into 0.6. Now solve it, you will get a equal to minus 6750 meter per second square. Now the resistive force. So average resistive force F equal to ma, m that is 0.04, a that is 6750. So you will get F that is 270 Newton. Here see, you will think like this, why the value of A is not substituted minus 6750? Because here in word I mentioned this thing, the resistive force. Resistive force itself is the force which is opposing the motion. Or suppose we write average force with negative sign, if this one is introduced, our force will be negative. The negative force also represents the same thing, it is opposing the motion. Clear to all of you? Now example 4.3. The motion of a particle of mass m is described by y equal to ut plus half gt square. Find the force acting on the particle. Okay? Force acting on the particle F that is equal to ma. So here we have to find the acceleration. the equation of displacement that is given to you. Now we know this thing. The differentiation of displacement with respect to time t will give you velocity, and then the differentiation of velocity again with respect to time t, that will give you acceleration. So let's start. The given equation, that is y equal to ut plus half gt square. Differentiate this equation with respect to time t. So v, that is dy by dt, d by dt of this equation ut plus half gt square. U, that is constant 1, differentiation of t raised to 1, that is 1, and half gt square, half g, that is constant 1, differentiation of t square, that is 2t, so 2 will be cancelled. So we will get u into 1 plus half g into 2t, so that is v equal to u plus gt. Now again differentiate this one with respect to time t, we will get acceleration. So now differentiating this equation with respect to time t, that is a equal to dv by dt equal to d by dt of u plus gt. Now this one is constant, its differentiation will be 0. Here differentiation of t, that is 1, so we will get a equal to g. Okay, so here when a equal to g, then simply we can write the force acting on the particle, that is F equal to ma, so that is equal to mg, because a, that is equal to g. Clear to all of you? Now dear students, the next topic, that is impulse. See, in our day-to-day life we observe some phenomena in which when the force act on the body for a short time, so at that time the short time interval and the time interval during which the force is acting, that is not measurable, but the change in momentum which is produced by that particular force, so that finite change in momentum, that is a measurable quantity, right? So see here, very simple example we can take here. When we see the cricket match, at that time we observe this thing, batsman hit the ball, so at that time the force acts on the ball, and that particular force act on the ball during very short time interval. The time interval, that is the time of contact between bat and ball. So force and time interval, that is very difficult to measure in this particular case. But actually that is not important also here. The important thing, that is the change in momentum of the ball, that can be measured. So here the product of force and time interval during which the force is acting, that is called impulse. So impulse, that is force into time duration, but force into time duration, that is nothing but change in momentum. So we can define the impulse like this: the product of force acting on the body and the time interval for which the force is acting, that is called impulse, and that is equal to change in momentum. Now we know, as per Newton's second law of motion, we have the equation F equal to dp by dt. So here if we take dt on left hand side, then we will get force into time interval for which the force is acting, and that is equal to dp, that is change in its momentum. So this one is called impulse or impulse of force, and the force acting here, that is called impulsive force. Now here impulse, that is equal to change in momentum. So suppose they ask you the question like this: write down the unit and dimensional formula of impulse. Then you have to remember this thing: impulse that is nothing but change in momentum. So unit and dimensional formula of impulse, that will be the unit and dimensional formula of momentum itself. Clear? Now example 4.4. A batsman hits back a ball straight in the direction of the bowler without changing its initial speed of 12 meter per second. If the mass of the ball is 0.15 kilogram, determine the impulse imparted to the ball. Assume linear motion of the ball. Now see here, we want to find impulse imparted to the ball. Impulse, that is nothing but change in momentum. So here we have to find the change in momentum in the ball. Now here we consider the direction from bowler to batsman, that is negative direction, and batsman to bowler, that is positive direction. So we can write here. Now as per given data, mass of the ball, that is 0.15 kilogram. As per our considered directions, we can say initial speed, that is in negative direction, so that is minus 12 meter per second, and final speed, that is plus 12 meter per second. Now here impulse imparted, that is nothing but change in momentum of the ball. So we can write here P final minus P initial. P final, that is mv final minus P initial, that is mv initial. So we can write m into Vf minus Vi. Now substitute the values. So mass, that is 0.15, final speed, that is 12, minus and initial speed, that is minus 12. So our answer, that will be 3.6 Newton into second. Clear? Now next topic, that is Newton's third law of motion. So Newton's third law of motion suggests this thing: to every action there is equal and opposite reaction. It implies that here we can understand this thing: the forces always acts in pair, right? So here if we say force on body A by B, that is action, then force on B by A, that will be reaction. But here one important thing, that is this one: there is nothing like that first action takes place and then after the reaction is there. It is not like that. The forces are in pairs. As soon as body A exert force on B, at the same instant B exert the force on A, right? And here either of these force can be treated as action, then other will be reaction. These two are equal in magnitude but opposite in direction. It implies that suppose we consider force on A by B as vector FAB, then if we represent force on B by A vector FBA, then according to this third law we can write FAB vector, that is minus FBA. Clear? So this one is Newton's third law of motion. Now example 4.5. Two identical billiard balls strike a rigid wall with the same speed but at different angles and get reflected without any change in speed as shown in the figure. What is 1. The direction of the force on the wall due to each ball, and 2. The ratio of the magnitude of impulses imparted to the balls by the wall. So here first we have to find the impulse and we have to find the direction of the force on wall due to each wall, means in both the cases. And then after we have to calculate the ratio of the magnitude of impulses imparted to the balls by the wall. Now see here, it is given to you when ball is reflected either in this case or in this particular case, the speed remains same one, right? So here first we think about this particular case. In this case, the ball is moving on x-axis and it is reflected on x-axis itself. So here, if we consider this particular first case, then here initial speed, that is in positive x direction, and after reflection the final speed, that is in negative x direction. So we can write here initial linear momentum of the ball, that is Pi equal to mvi, but v, that is equal to u here, right? Notation is used u, so we can write mui caret, and that is in positive x direction. Okay, now x component here, that we can take Pix, that is mu, and the motion is in x direction, so y component, that is 0. Now if we consider final linear momentum, so after reflection it is moving in negative direction, so we can write P final, that is mvf equal to minus mui caret. Okay, now here if we take x component of final momentum, that is pfx equal to minus mu. Again the motion is in x direction, so y component of final momentum, that will be equal to 0. Okay, now here we have to find the impulse, means we have to find the change in momentum of the ball. So change in momentum, that is final momentum minus initial momentum. So here now we can write impulse, that is change in momentum, that is final momentum minus initial. Final momentum, that is minus mui caret, minus initial, that is also mui caret. So you will get minus 2 mui caret. So here x component of change in momentum, that is minus 2 mu, and y component of change in momentum, that is 0. Clear? So here we can say this thing, force on ball by wall, that is in negative x direction. This negative sign here, see, you are getting the impulse, that is change in momentum, that is in negative x direction. So we can say force on ball by wall, that is in negative x direction. So as per Newton's third law of motion, we can say force on wall by ball, that is in positive x direction. Clear to all of you? Now magnitude of the impulse, that is in x direction, is 2mu, right? But it is in negative x direction, so magnitude wise simply we can write that is 2mu. Now in second case, ball hit the wall at angle 30 degree with negative x axis. So now in that particular case we have to calculate the impulse. So see the case. Here the ball hit the wall at angle 30 degree with negative x axis and reflected or rebound at the same angle in downward direction with same angle 30 degree with negative x axis. So here if we take the components of initial and final speed, then that will be as shown in the figure. Now see here, initial linear momentum of the ball Pi, that is here mu cos theta I minus mu sin theta j, because this one is in negative y direction, this component is in positive x direction. Then after the x component here we can write, that is this multiple of I caret mu cos theta. Then y component of initial momentum, that is mu sin theta with negative sign. So this one. Clear? Okay. Now final linear momentum. So see here, the velocity component in x direction, that is minus u cos theta I caret. In y direction, that is minus u sin theta j caret. So final linear momentum, that is minus mu cos theta I caret minus mu sin theta j caret. So here we can say this one is the x component of final linear momentum. This one is the y component of final linear momentum. So P final x component, that is minus mu cos theta. P final y component, that is minus mu sin theta. Now we have to find the change in momentum to calculate impulse. So change in momentum, that is final linear momentum minus initial linear momentum. So P final minus P initial. So P final, that is this one, minus mu cos theta I minus mu sin theta j. Initial, that is mu cos theta I minus mu sin theta j. But when we implement this negative sign, we will get minus mu cos theta I plus mu sin theta j. So these sign components will be cancelled. Clear? So resultantly here we can write minus 2 mu cos theta I caret. Theta is given to you, 30 degree. So we can say that is equal to minus 2 mu cos 30 I caret. Again here, this minus I caret represents the negative direction. So we can say here force on ball by wall, that is in negative x direction, right? And here, as per Newton's third law of motion, force on wall by ball, that will be in positive x direction. Now here magnitude of impulse, that is 2 mu cos 30, and that is in negative x direction. So we already discussed this thing, force on ball by wall, that is in negative x direction, and as per Newton's third law of motion, force on wall by ball, that is in positive x direction. Now in second question, we have to find the ratio of the magnitude of impulses in both the cases. In first case, the magnitude of the impulse was 2 mu. In second case, magnitude of the impulse, that is 2 mu cos 30. Clear? So here that is 2 mu cos 30. Clear? So now let's calculate the ratio of these two. Okay? Now see, ratio of the magnitude of impulse is 2 mu upon 2 mu cos 30. So these 2 mu will be cancelled. 1 upon cos 30, that is root 3 by 2. So our answer, that will be 2 by root 3, and if we solve it, it will be 1.2. Clear to all of you? Now, dear students, the next topic, that is conservation of momentum. So, what is the meaning of conservation of momentum? Conservation of any physical quantity means the quantity remains constant. Okay. So here conservation of momentum means the total linear momentum of an isolated system that remains constant. Now isolated system means what? Isolated system means such a system for which the net external force acting on it, that is equal to 0. So in other words, we can say this thing: if the net external force acting on the system is 0, then the total linear momentum of the system that remains constant. Now let's understand this thing with the help of one simple example of bullet which one is fired from gun. So initially bullet is loaded in the gun. At that time the system which one is made by two constituents, bullet and gun, both are stationary. So here we can say this thing: initial total linear momentum of the system, that is 0. Now as soon as we fire the bullet, the force by the gun on bullet, that is suppose F. Then as per Newton's third law of motion, the force on gun by bullet, that will be equal in magnitude but opposite in direction. So we can say that is minus F. Suppose both these forces acts for a time interval delta t, or we can say during time interval delta t. Then here first we can write, if we consider the initial linear momentum of bullet, that is PB, and gun, that is rifle. Okay. So if we consider the linear momentum of rifle, that is PR, then both are stationary initially. So we can say for bullet momentum is 0, for rifle or gun it is 0. So we can write PB plus PR, that is equal to 0. Now bullet is fired, external force is not acting, the interaction takes place between the constituents of the system. Okay. So here when force F is acting for time interval delta t, then we can say the change in momentum of the bullet, that is the impulse on the bullet, that is F delta t, that is final linear momentum minus initial. Suppose after firing, the momentum of the bullet, that is PB dash, then we can write F delta t, that is impulse, and that is equal to PB dash minus PB final minus initial, but initial is 0. So directly you can write that impulse F delta t, that is PB dash. Now change in momentum of rifle or gun, that is also impulse. So force, that is minus F, time interval, that is delta t. So minus F into delta t, that is impulse on gun or rifle. So that is the change in momentum of the rifle. Okay. Now initial momentum of the rifle, that is 0. So whatever is the final itself is the change. So we can write PR dash, change in the linear momentum of the rifle, that is the final linear momentum of the rifle, PR dash, that is minus F delta t. Now if we take the summation of final linear momentas of bullet and gun, or we can say rifle, then that is PB dash plus PR dash. But PB dash plus PR dash, that is equal to F delta t minus F delta t, and that is equal to 0. So here we can observe this thing: the final total linear momentum of the system, that is the final linear momentum of a bullet plus gun or rifle, that is equal to the initial total linear momentum of a bullet plus rifle or gun, and both are 0, it implies that the total linear momentum of the system before firing the bullet and after firing the bullet, that remains same one, that remains constant one, and this thing is known as conservation of linear momentum. Clear? Now next topic, that is equilibrium of particle. The condition in which the net external force acting on the particle that becomes 0, then it is called equilibrium of forces. So if two or more than two forces are acting on the particle, then the net force or resultant force acting on the particle, that is the vector summation of all the forces. And when this vector summation of all the forces, that is equal to 0, then we can say the net force of all the external forces acting on the particle, that is 0, and now we can say the particle is in equilibrium. Now see here, equilibrium means what? When net force is acting on the particle is 0, it implies that as per Newton's first law of motion, we can understand this thing. If the particle is stationary, then it will remain stationary. Or if the particle is in motion, then it will continue it with uniform velocity. Means in both the cases, the acceleration will be equal to 0. Now see here, net force acting on a particle, that is nothing but vector summation of all the forces, that is equal to 0. Clear? So here equilibrium, for equilibrium sigma f, that is equal to 0, then we can say equilibrium will be established. So we have to take the vector summation of all the forces to find out the net force. Suppose we consider three forces are acting, then in that particular case, here the summation of x component of all the forces, that should be equal to 0. Summation of y components of all the forces should be equal to 0, and summation of z components of all the forces should be equal to 0. Then and then only the vector summation of all these forces will come to 0, otherwise not. Now here suppose we think about two forces acting on a particle, F1 and F2. Now when two forces are acting on a particle, then what will be the condition for equilibrium? So vector summation of F1 and F2, that should be equal to 0. It implies that F1 plus F2 equal to 0. So we can write mathematically F1 equal to minus F2. So in other words, we can say when two forces are acting on a particle, and if these two forces are equal in magnitude and opposite in direction, as shown in this figure, then and then only there will be the equilibrium of particle, because in that case the net force acting on the particle will be 0. Suppose three forces are acting on the particle. Then when three forces are acting on the particle, then if we take the vector summation of all these three forces, F1 plus F2 plus F3, then for equilibrium that should be equal to 0. So here the vector summation of any two forces that should be equal in magnitude with the third force and that should be in the opposite direction of third force. See here, this one is force F1, this one is F2, this is F3, and on this particular particle, these three forces are acting. So here these three forces are passing through a common point. So when all the three forces are here to the common point or acting at the same point, then the forces are known as concurrent forces. Then see here, if we take first F1 plus F2, then magnitude of F1 plus F2, that should be equal to magnitude of F3, and F1 plus F2 should be in the opposite direction of F3. Then and then only the resultant force will be equal to 0. And here, if we think about the equilibrium of particle when more than two forces are acting, at that time we can observe this thing. If we take the vector summation, then in graphical method, if you remember, we discussed this thing. To take the summation of the vectors, we arrange the given vectors head, tail, head, tail, head, tail, head, tail. So if more than two forces are acting on the particle, and if we arrange them in head, tail, head, tail, head, tail manner, then definitely it will form a closed loop. And if all these forces acting on the particle are arranged head, tail, and form a closed loop, then we can say this thing, the resultant of all the forces will be 0 and equilibrium of the particle will be there. Now here we can represent this thing in the broad sense like this. If n forces are acting on the particle, then if vector sum of all these n external forces that is equal to 0, then the equilibrium of particle that will be obtained. Clear the concept of equilibrium? Now example 4.6. See figure. A mass of 6 kg is suspended by a rope of length 2 meter from the ceiling. This one is the case. A force of 50 Newton in the horizontal direction is applied at the midpoint P here of the rope as shown. What is the angle the rope makes with the vertical in equilibrium? Take G equal to 10 meter per second square. Neglect the mass of the rope. Now see here, if we consider the figure, now at this particular point 50 Newton force is acting in the horizontal direction due to mass suspended at this end of the rope. There will be the weight of this object in downward direction. So here we can say this thing, the tension will be produced in this upper part of the rope as well as in lower part of the rope. And suppose here the angle made by the rope with vertical in equilibrium position, that is theta, and tension in upper part, that is T1, and tension in lower part, that is T2. So here we already discussed this thing. For equilibrium, the vector summation of all the forces should be equal to 0. And in other words, we can say this thing, the summation of x components of all the forces should be equal to 0, and summation of y components should be equal to 0. Clear? Or in other words, we can say the forces which are acting in x direction should balance each other and should be in opposite direction to each other. Forces in y direction also balance each other and are in opposite direction, right? So here we can write from the figure T1 cos theta, that is equal to T2, but T2 that is weight, and weight that is mg, that is 6 into 10, that is 60 Newton. So we can write T1 cos theta, that is T2, that is 60. And in x direction, T1 sin theta and 50 are in opposite direction. So both should balance each other. So we can write T1 sin theta, that is 50. Okay. Now take ratio of this to T1 sin theta upon T1 cos theta. So that is equal to 50 by 60. T1 will be cancelled here. This portion will be cancelled. So sin theta upon cos theta, that is 5 by 6. This one is tan theta. Tan theta is 5 by 6. Now if we find out theta, that is tan inverse 5 by 6 in the table of natural tangent in log table, then we will get theta, that is equal to 40 degree. Clear?